So hello, everyone. The speaker today is Anna Sung, and the title of her talk is Generalized Morse Theory for distance functions to surfaces for persistent homology.
Yes, so hi, everyone. First, thank you really to the organizers for the invitation. It's really a great pleasure to be giving this talk today. And so this is work, joint work with Ambrose and Anthea, my math supervisor, and they are both online. So once we will have the questions, we can answer together, of course. So as you said, so we have worked to generalize Morse theory to distance functions, and especially those defined with respect to surfaces in the context of persistent homology, because we want to use persistence to understand the notion of shapes and especially shape textures. The starting point behind the project is that in my biology lab, because I'm also doing my PhD jointly between mathematics and biology. So in the biology lab, they have lots of really beautiful vascular data. As you can see here, they're really interesting morphologies of tubules branching and merging together. So mathematically wise, it's really like difficult to describe what is happening there. The same can be said about sponge's bone, where you have combinations of rods, platelets. In the endoplasmic reticulum, it's mixtures of tubules and membranes, and so on. And one major question motivating kind of even the mathematical side of my PhD is how a certain type of blood cancer called AML, leukemia, how does AML remodel the bone marrow vessels? As you can see, whether you are in a control stage or once the disease has started to engraft, the patterns in the shapes, the patterns in the vascular shape is totally changed. Actually, you go from smooth, regular, thick vessels to thin, leaky, roughly very rough aspects of the vessels after progression of the disease. So really the aim behind this is that the patterns, because the patterns reflect the state and the properties of your system, how us as mathematicians can we understand this? So for today, the talk will be mainly theoretical. So first, I will start with SDPH, so sign distance persistent homology, so the method that will be used to quantify shapes. And we actually we'll see that we need to generalize Morse theory to distance functions, because Morse theory is something that is historically has been defined for smooth settings. Then coming back to SDPH, we'll be able to give a rigorous interpretation of the outputs of SDPH, which are the diagrams. And finally, I move on to explaining how we can use it for real-life applications, especially vascular analysis. So first, what is assigned distance persistent homology? This is quite simple to describe. So you take a 3D shape, like vessels, and you obtain a binary segmentation of that vessels. Then you convert this to a sign distance field, and you take the sublevel sets and consider this as your filtration. So what happens is that first you have disconnected bits of shape. Then later on in the filtration, these bits connect together to form loops. And then later on, the loops get filled out because the entire cube will be filled. So then you compute persistence on that filtration. For those of you who are maybe not that familiar yet, so you obtain persistence diagrams in dimensions 0, 1, or 2, depending on whether you're studying topological features like components, cycles, or cavities. And persistence is about capturing the algebraic relationships between the lifetimes of these topological features. In fact, the way I presented it is formulated in terms of discrete cubical settings. And SDPH already appeared in multiple papers in the discrete setting, especially for the study of porous rocks, porous materials, and also sponge's bone more recently. Here, however, we are interested in first the understanding in a kind of smooth setting, more precisely in the setting of distance to smooth surfaces. So consider that you have a bounded open set, omega minus, with ck smooth boundary where k is greater than 2. So you have your space that is divided into three regions: the surface, the inside, and the outside. Then you define your sign distance as the function that to each point in space assign the distance to the surface, but with a minus sign if you're located inside, and with a positive sign if you're located outside of the binary object. Then you define the sublevel set filtration, and then you compute the persistence diagrams. But wait, are these persistence diagrams even well defined, in the sense that is the persistence module derived from the sublevel set filtration decomposable into a sum of persistence intervals? The second question is, how can we interpret these SDPH diagrams? And also, are they truly quantifying shapes and also patterns in shapes? Let me recall first the link between persistent homology and the smooth Morse theory. So Morse theory is about the study of non-degenerate critical points, and especially of smooth functions. Being non-degenerate means here that your gradient cancels. However, the Hessian is non-singular, non-zero determinant. So at such points, your function can be rewritten into a normal form that involves a number, lambda, which is the Morse index. So below, I'm giving some examples for 2D functions defined in 2D, where you have locomins, locomaxes, and saddle points. In fact, Morse theory will help us to interpret the SDPH diagrams. For now, I'm still talking about the smooth setting. So Morse theory relates smooth proper Morse functions to their persistence diagrams, because you have two very well-known lemmas, the isotopy lemma and the handle attachment lemma. Basically, the isotopy lemma says that when you increase the level and you take the sublevel set, when you are not encountering any critical point, then nothing changes at the level of topology and homology. However, as soon as you're crossing a non-degenerate critical point of index lambda, topologically, this is equivalent to attaching a lambda dimensional handle to the previous smaller sublevel set. In terms of homology, this either creates a new class in dimension lambda, or it will kill a pre-existing class in dimension lambda minus 1. So typically, the birth and the death in the persistence modules will correspond to critical values that themselves correspond to critical points with indices differing by 1 unit. Okay, the problem here is that distance functions, even those generated by smooth boundaries, themselves as functions, they are not smooth, especially on the medial axis and the cut locus, which is the closure of the medial axis. As you can see here, when you sample the sign distance function along the vertical axis, the arranged bits are on the medial axis, and you can see that it's actually not smooth. So the question is really our motivating question: can we build or generalize the two Morse lemmas to sign distance functions? To do that, first, there's a notion of critical points. That notion has been known for quite a long time already, especially in the Riemannian setting, thanks to Grove, Shiohama, and Shiger, and also more recently in the Euclidean setting, thanks to Liotier. So these points are those at which an extended gradient field vanishes. That extended version coincides with the classical gradient when you're outside of the cut locus, and where the iconal equation is valid, saying that your gradient has unit norm. But on the cut locus, then your norm is actually compressed between 0 and 1 in the large sense, so there's a typo here. And where it vanishes, you actually have the critical points. Geometrically, what it means is that your point X is surrounded by pieces of surface. So more precisely, actually, X is critical as soon as it belongs to the convex hull spanned by the connect points. The connect points here being the closest points located on the surface. So equivalently, you can also rephrase it by saying X should coincide with the center of the unique smallest closed bow that contains all the connect points. So the first good news is that, yes, the isotopy lemma can be generalized to sign distance. The reason actually, for us, it was quite a straightforward extension of a pre-existing result, because Grove and Shiohama precisely define the notion of critical points in the Riemannian setting precisely to make the isotopy lemma work. And so the idea is that they proved that you can find a gradient-like vector field that kinds of always points in the right direction, strictly in the right direction. And so, so that the interlevel set can be shown to be homomorphic to sort of cross product like a band. So then you can retract the bigger sublevel set related to B, retract it until going to A. So they are homotopy equivalents. So far you are not using any notion of non-degeneracy or index. So how about the handle attachment lemma? How can we define the notion of index? What is interesting is that in Grove and in these the other references, they were saying there exists a notion of index, but only in certain special cases, and they do not know what to do about it. So the right framework for it is the CK-mean-type framework that was introduced by Jaschkovic and Rubinstein. Actually, CK-mean-type functions are those that are locally of the form a minimum of finitely many CK-smooth functions alpha i's. So typically the kind of profile you have is that you are mostly smooth, but you have a peak at points where you are not smooth. So such functions actually have a good notion of non-degenerate critical points, and they do admit a normal form, but here up to homeomorphic transformation of the domain. So the idea here is to recast distance functions as CK-mean-type functions. And one useful geometric condition to do so is the strict ball condition. Namely, it says that your point X, so you find the connect points on the surface, and at any of the connect points, the curvature of the surface should be strictly different. So here should be strictly smaller than the curvature of the contact ball. In other words, your surface should not wrap too closely your contact ball. So this corresponds to condition B, and another condition A, namely that X has finitely many connect points. Together with B, they are sufficient to express the distance function as a CK-mean-type function. So what it means here is that the alpha i's that are used in that CK-mean-type representation, these alpha i's correspond to distance functions to pieces of surface. On the right-hand side example, whether you are considering the full distance function or whether you're considering the minimum of the distances to the pieces of surface containing each one connect point, then these two coincide. This is the same in the neighborhood of X. They cannot see the difference. It's interesting to compare this to the distance to a finite point cloud, as studied by Bobrowski and others, especially in the context of Čech complexes. So, because as you know, at each scale of the filtration, Čech complexes are homotopy equivalent to sublevel sets of the point cloud distance function. So for point cloud distance function, they are always CK smooth outside of the point cloud, and A is already satisfied, of course, but B, isn't really well defined. So yeah, it's interesting to compare here. We can define now the notion of NDG points, but in the mean type sense for distance functions. So we still suppose that A and B hold. Then X will be NDG if and only if three conditions hold. Namely, first, that the connect points are in general position. So they span n-1 dimensional subspace in your Euclidean space. The second condition says that X should belong strictly to the inside of the convex hull of the connect points. And the third one states that the restriction of your function to the stratum of medial axis on which X is sitting, so that restriction should be a Morse function in the classical sense. So in the sense that the Riemannian Hessian shouldn't vanish. At the bottom, I'm providing examples where each of these conditions, C, D, E, are violated. especially when you are not respecting condition E. What you can see is that when you increase the level and you take the sublevel set, so whether you increase from the outside or increase from the inside, nothing changes topologically in the sense that there is no handle attachment, and this is not what we want. However, if you are respecting these conditions, then you are non-degenerate and you can define a notion of index. So for the pure distance function, the distance to the surface, if you call mu the index, it involves two terms in it. The first term is the dimension of the subspace spanned by the connect points. So in the left example, you have two connect points, which means the first term becomes 1. The second term involved in the index is actually the index in the classical sense of the restriction. So on the left example, again, here you have a local maximum when you restrict your distance function on the arranged medial axis. And so it contributes to the term 1. So this means that mu in total will equal to 2. And then lambda, the index with respect to the sign distance, is defined relatively to the mu. So it's equal to mu if you are located outside, and n minus mu if you're located inside, n here being the dimension of the space. So again, here it's useful to compare to the point cloud distance. So let me come back to the previous slide. For point cloud, distances A already holds, B not really defined, and the only requirement for points to be NDG is C and D. E is always satisfied because here the stratum of medial axis corresponds to the Voronoi cell on which X is located, and it's always local min there. So the index of the restriction contributes to the term 0. So the index there is only m minus 1, the first term. So now that we've managed to recast distance functions as CK min type functions, and now that we have a notion of index, we can use Jershkovich and Rubinstein's framework to show that the normal form is also satisfied at non-degenerate critical points. And so here we are really tempted to hastily jump to the conclusion that, yes, the handle attachment can then be extended to distance and sign distance functions as well. But actually, there's a lot of trouble here, because when you take the classical proof given in Milnor for the handle attachment, it's actually not trivial to try to glue what happens inside of the neighborhood where the normal form holds and what happens outside of it. So the missing piece here is topological Morse theory. And curiously, we didn't find that many papers dealing about topological Morse functions. These are functions that admit only two types of points: either your regular, so f can be written in a linear-like form, or your NDG in the topological sense, and then f can be written in a normal form, up to homeomorphisms of the domain. So especially we didn't find papers dealing with a handle attachment in the form that we need, except in a single paper by Kirby and Ziebenman, but they do not provide any complete proof. They only vaguely mention it as a side remark, some proof based on mutually transverse foliations, based on some work done by Ziebenman. So we prefer to provide here more like a simpler proof, providing very purely topological arguments, and also quite similar to what you can find in Cantwell and Krovalek. So there's a topological counterpart to the isotopy lemma. So we showed it by saying that you take arbitrary values between two values A and B. So you take arbitrary C, and you can always find a small enough epsilon so that the interlevel set stuck between C minus epsilon and C plus epsilon, that interlevel set can be covered by a finite number of open subsets. And the strategy is to actually deform your space by applying successive small deformations happening only in these small opens finitely many of them, small open subsets, and you lower the values at with a strictly non-zero amount of decrease unless you hit the bottom C minus epsilon. You can extend that argument to the whole interlevel set between A and B. So that's how we showed it for this. And then you can also show the topological version of the handle attachment. So here the proof really looks like the classical proof. You consider a neighborhood of the point on which the normal form is true, and then you build an auxiliary function on which you can then use the topological isotopy lemma. And so you can express the B sublevel set as you retract it onto the A sublevel set together with a handle, and the handle itself can be further retracted into a lambda cell. So yes, we arrive at our generalized handle attachment for sign distances, namely if you have an interlevel set only containing a single non-degenerate point and all other points are regular, then when you pass the level, it's equivalent to attaching a lambda cell. You can also generalize if in your critical level you have more than a single point, but you have several NDG points, then you are attaching all the handles. So you prove it by combining what I just talked about on the topological Morse versions, and together with the knowledge that the mean type framework gives you a normal form at your point. So now we've kind of found the right geometric conditions so that first you can recast your distance functions into CK mean type functions, and then starting from there, you can generalize the Morse lemmas. But the question is, are these geometric conditions restrictive? Because when you, I will not come back to the slides, but what you can see from the conditions A, B, C, D, and E, actually they are in particular forbidding perfect configurations like cylindrical necks or spherical caps, like those where you have infinite number of connect points. So actually we derived a very strong result, which says that for nearly any way of embedding your surface, so now you're requiring slightly smoother surface, K greater than 3. So for generic embeddings of your surface, the associated sign distance function only admits a finite number of critical points, and all of them being non-degenerate. So this is actually a very strong result because it states that essentially in terms of applications, for nearly any 3D shape, any binary object you want to analyze, the sign distance persistent homology module can be decomposed into a finite sum of burst depth intervals. And furthermore, you actually know where to which types of points these burst depths correspond to, thanks to the Morse theory. And to show that genericity result, we resort to transversality theory. So the main ideas are that being transversal in mathematics is something generic. So transversality between a map and a space means that basically you've got this equality. So the sum of, so your map is sending the tangent space of your original space to some space complementary to the tangent space of W, and these together span the whole tangent space of Y. So if you look at the examples at the bottom to give some more concrete illustrations, this is non-generic for two curves to cross in a tangential manner. However, this is generic for them to cross in a neat way, not tangentially. And it is not generic that two curves in 3D have an intersection because 1 + 1 is strictly smaller than 3. So what is generic is that these two curves have empty intersection. And likewise, it is generic to have only a finite number of connect points, as was shown by Yomdin, and it is non-generic to have, again, infinitely many connect points. And as our last example, it is actually generic to be inside strictly inside of the convex hull as soon as you are belonging to the convex hull, and it is non-degenerate to be exactly lying on the boundary of your convex hull. So the proof is rather like complicated, let's say, but the idea is you show that each of the properties can be rephrased as a transversality relationship between a carefully constructed map F parameterized by an embedding and a subspace W that is also carefully chosen. And here we also rely on the generic description of the cut locus, thanks to literature that due to Matter, Giblin, and so on. So I just checked my time. Okay, 26 minutes. Yeah, I hope that it's been relatively clear, but if not, you can jump in and ask your questions. But if you don't have any question, then I can move on to explain how then now we can use generalized Morse theory to explain and interpret our SDPH diagrams. The first...
Yeah, I do have a question. Is that okay? You asked if
of course.
questions.
Sorry.
Can you go back to the slides where you were talking about handle attachments and isotopies?
This one?
That one and the previous one, because I mean, I believe that in dimension 4, there's a very different situation as to dimensions higher than 4. So what I guess my question really roughly is, how are you considering how this changes with dimension? Because in dimension 4, you can have these wild things called Casson handles that are like, you know, have infinitely many different little bits that are sticking out. Yet, you know, topologically, they're just a regular handle. So there's a very subtle issue there in dimension 4. So I was wondering what exactly are you solving here if that's not like a problem for you?
Yeah, so actually, well, I didn't know about this important subtlety for dimension 4, but here the proof kind of says you construct an auxiliary function based on the original function small f, and your bigger function, I mean, your big F function, you define it in such a way that outside of a neighborhood, all functions coincide, then the bigger sublevel set also coincide. However, what is different is the smaller sublevel set. And so here there's, it's just about expliciting the construction. And then it appears that the smaller sublevel set, so related to C minus epsilon for the big F, is actually truly the union of a region of space, which is the handle, and attached to the smaller sublevel set of the relative to small f. And here there's no consideration of the dimensionality. Yeah.
Well, okay, but in dimension 3, I think is fine, and probably in dimension bigger than 5 as well. But I'd recommend you check out, you know, Friedman and Quinn's work on dimension 4. Like the whole point of Friedman's Fields model was kind of this problem.
If you don't mind, can you write the names of the paper you're referring to, or the
It's Michael
phenomenon.
Friedman. He's a Fields medalist.
Okay. Yeah, thanks a lot. So hopefully our proof is correct, but truly here the ingredients are very, very basic. So yeah, we'll have to check. So coming back to the part 3, which is about how we can now use the generalized Morse theory to interpret SDPH diagrams. So the first thing we do is to classify the critical points depending on their generalized Morse index lambda, as well as the sign of the sign distance d, which means whether you are located inside or outside. So we are able to identify 6 types of critical points, and among them 12 subtypes of critical points. At the bottom, I'm showing you some examples of different subtypes. So you have to multiply by 2 to obtain the 12 subtypes, depending on whether you're located inside or outside of the binary object. But then you can see, for instance, that some of the critical points corresponds to bumps, some others to bottlenecks. And you can also classify the persistence birth-death pairs thanks to the knowledge that you're pairing points between of indices lambda and lambda plus 1. And you obtain 7 types of pairings. So in terms of the diagrams, you are having, once you compute the SDPH diagrams, you obtain a scatter plot dispersed throughout these quadrants. So as a remark, the distance of the birth-death points with respect to the main axis should be greater than the reach of the submanifold. Also, this is cool in theory, but what can we say to biologists in practice? How can we interpret the diagrams? So in the context of vascular analysis, you can have a kind of picture of what happens with respect to the critical points and also with respect to the pairings. For instance, in the blue quadrant, you can measure undulations in thicknesses of the vessels. In the red quadrant, you can measure how heterogeneous the loop sizes are across your network. In the green quadrant, you can measure a notion of sparsity given by the sizes of your cavities, for instance. For example, in the red quadrant, if you have networks featuring more and more heterogeneous loop sizes, then you can see an increasing dispersion in the vertical direction of the birth-death points. This is explained by the fact that you're pairing points carrying values that are more or less different in terms of death time. But the take-home message truly here is to say that the SDPH diagrams are quantifying the texture of shapes thanks to the patterns of association between critical and destroyer, critical points and values. Here I'm showing some SDPH diagrams computed on 5 synthetic shapes generated with the curvatubes model, which I designed in the first half of my PhD. And what's interesting to see is that even if by eye, it's not really easy to describe how different, how much differences and what types of differences you can find between, say, the row number 2 and row number 3, SDPH is able to discriminate between them quite easily. And you can also apply the previous morphological interpretation on each of these diagrams to retrospectively explain the shapes. Here I'm showing some shapes also synthetically generated, however, based on the same generation parameters so that the texture is the same or very, very similar. And not surprisingly, but the good news is that SDPH will be blind with respect to the actual geometric realization of the shape, but the information that SDPH captures is the texture of the shape through the persistence diagrams. And as you can see, they are looking quite alike. Also, by slightly changing the generation parameters, we saw that the SDPH diagrams are only changing slightly as well. So we are led to conjecture a sort of stability theory, maybe for SDPH with respect to texture. Maybe as you can, maybe if you know, the classical stability theorem in persistence says that if your 2 functions are closed in infinity norm, then their diagrams should be closed in terms of bottleneck distance, for instance. But here it's a stronger result. If your shapes, even if they do have a very large distance in terms of infinity norm, their diagrams are still very close to each other, at least empirically. So it would be interesting to explore in the future whether or not there's a new notion of stability with respect to texture involved here. And to finish, my last part is about how we can use this framework to understand vessels, especially in the context of leukemia. So I spent a huge amount of time understanding how to segment these shapes. Just the fun fact here being that each 3D image is a confocal image weighing up to 300 gigabytes. So just to be able to exploit them was in itself quite a challenge. So I segmented these shapes and computed diagrams on them. And here I'm showing 3 examples where you have a control sample, no disease, sample at the early stage of engraftment and one at the later stage of engraftment. And when you look at the diagrams, even if the differences are quite subtle, still you can extract some useful information. For instance, in the early stage, you have a lot of angiogenesis happening, so mostly thin vessels, small and dense loops. In the later stage, you still have thin vessels, but with much sparser networks. And importantly, you have also more heterogeneous distribution of loop sizes across the network. One thing we tested is, can we emulate this behavior on synetic shapes? So partially yes, because we are able to exaggerate the behavior that I described above, but actually we shouldn't expect a perfect emulation for the reason that real data is always a mixture of perfect behaviors. In terms of texture, real data is always a mixture of pure textures. So what's practical with SDPH is that you can actually locate the critical burst depth voxels or critical points, and then you can also specify in which region in space you want to compute the SDPH diagrams. And we did see some correlation between some spatial features related to the local diagrams and, for instance, the location of the cancer cells. Before I conclude, I just make some small advertisement for the curvatubes model that can be useful to simulate porous shapes. And you can also design mathematical methods on it. You can also use it just for fun and play with the parameters. To summarize, we generalized Morse theory to distance functions by following this route. So first you take the distance functions and find the right geometric conditions to frame them inside of the min-type framework. Then this provides us with a normal form at NDG points, and then you work with the topological Morse lemmas, so that's how you generalize it. Furthermore, as an important result, the sign distance functions are generically Morse. In the second part, we showed that SDPH quantifies shape textures as opposed to the notion of structuring shape, which I believe is a complementary piece of information. And we saw how to use Morse theory to interpret these diagrams, especially for real-world applications, where you can also now decompose your spatial mixture of textures into pure textures. And finally, maybe of course, there are much more to explore here, but maybe there's a kind of new notion of stability involved here. So I would like to thank both of my thesis teams in the team of Anthea and Dominic. And also I would like to thank my collaborators and many researchers I've been lucky to talk with. So you can find some references here, and thank you for your time. Thank you for watching.
Thank you so much. So I would invite everyone to unmute themselves and thank Anna for a very nice talk. Okay, so now it's time for questions.
Hello.
Hello.
I have a question. So thank you for the very nice presentation, Anna. It was very clear. So I've been working on the same problem for some time, not exactly the same. So I've been wondering about, it was the first or the second chapter of your presentation, about the isotopy lemma you had, like the small homotopy preserving lemma you had, like between the C minus epsilon and the C plus epsilon sublevel sets. Not this one, not the...
Oh yeah, the isotopy.
Yeah, the isotopy.
Oh yes, sorry.
Like describe
yes.
how you managed to obtain it. So yes.
Yes, so there are two ways. So the kind of easy way is to reapply the results proven by Grove and Cheeger. So they are already phrasing the isotopy lemma for pure distance functions exactly in the desired form. So for us, it's just a matter of saying the sign distance is the same if A and B are both positive or both negative. And if you want to work close to the zero value, you know that the sign distance is actually CK. So you can just like retract like that. So this is the first way to prove it. The second way is to actually prove it as a consequence of the topological version of the isotopy lemma. But actually, that's not so different in the sense that the topological version actually uses at the heart of it the same arguments as Grove, based on the gradient-like vector field. So I hope that this answers your question.
Yes, okay, it does. I may have another question. So you need like the CK condition, the CK condition on the,
yes.
the surface. Like, so this is the reason why the K has to be greater than 3.
Okay. So the thing is, K greater than 3 is needed for the genericity result in R3, and K greater than 2 is needed for the generalized Morse theory without the genericity result.
Yeah, okay, so like the distance function has to be differentiable twice or something like that.
Twice continuously, because it's not enough to be why it's so important. Actually, for instance, I think there are some papers dealing with C11 Morse functions or things like that. But for us, we need a CK, K greater than 2, for the reason that as soon as K greater than 2, you have the CK smoothness when you are in a tubular neighborhood of your surface. I'm not totally sure about what happens if you're less smooth, to be honest, but I know that there are traps there.
Okay. Well, thanks a lot.
Thank you to you.
More questions for Anna?
I have a quick one. That was a great talk. I had to step out for a second to take a call. I'm really sorry, so I might have missed that. How stable is this whole approach with respect to the segmentation at all? So if you wiggle the segmentation a little bit. Yeah.
Yes, very good question. So actually, okay, so first, everything is always sensitive to segmentation. But the thing is, the segmentation here is good enough so that, of course it's sensitive, but in that particular case, because the images, the original images are relatively clear and neat, it's relatively okay to reconstruct the segmentation. But definitely, so what happens is, imagine you have slight disconnections between parts of vessels. So because you are considering a filtration, you can imagine that because the disconnection is very slight, you can soon after the 0 level, you increase and they join together. So somehow it's as if you're kind of delaying the moment they are considered as joined. Yeah, I think it's relatively okay. It's not really a good scientific answer, but I mean, in practice, I think this is quite good, yeah.
No, this is really great. Thanks so much. That's amazing.
Thank you.
Further questions for Anna? So in case not, then I'm going to stop the recording here. Thank you so much again, and we're going to take all the questions offline.
Thank you so much.